What I would like to be able to do is now use this let's look at some problem like this. Okay, let's say you have 5-kilogram object connected over a pulley to a 2-kilogram object, coefficient of kinetic friction 0.4, and let's say the height here is 3 meters. And I would like to ask questions about this situation. What's going to be the final velocity of the 2-kilogram object when it hits the ground? What's going to be the velocity of the 5-kilogram object? And how much time is it going to take them to hit the ground? What's the acceleration of the system? However, if I just ask the problem this way, you could have already done this 6 weeks ago using Newton's laws. So I got to add something to make it worthwhile your time. I mean, you've been here 6 weeks longer, okay? So I'm going to add the fact that the pulley has mass, okay? Let's say it's a heavy pulley, 1 kilogram. And it has radius, let's say 0.8 meters. So what makes this a chapter 10 problem is that now the pulley is no longer negligible. Its mass is no longer negligible. It has mass, it has size, and I need to give you its shape. Now usually if the problem doesn't give you the shape of the pulley, assume that it's a solid cylinder. Because usually that's most pulleys is a shape like this, the string is going over it, okay? And then looking at it from the side, it just looks round, and it's a solid cylinder. So you would use the moment of inertia of a cylinder rotating around an axis going through the center. Okay, but the problem could say, for example, that instead of a solid cylinder, it's a spherical pulley, solid sphere. Okay, it could be like a bowl, has a little groove in the center, and the string sits over that groove, so it could be a spherical pulley. Okay, so let's just say it's a solid spherical pulley. So now solve the problem. Tell me, what is the acceleration of the system? What is the time that it's going to take to hit the ground? Everything. I want to know everything. Okay. So let's set up the equations now. We have the weight of this, which is 19.6 newtons. We have the tension T. Now, what's going to happen here that is different than the previous chapter 5 problem is the tension on this side of the string is going to be a little bit heavy, higher than the tension on that side. This one is going to be T1. This one is going to be T2. And T1 is going to be greater than T2. The reason why I know that is because I know that the pulley, if I look at the pulley for a second, there are two forces competing on the pulley, T1, T2. And this T1 is trying to make the pulley rotate clockwise. T2 is trying to make it rotate counterclockwise, okay? And I know that at the end, T1 has to win because the 2-kilogram block has to come down, and the 5-kilogram block has to go that way. So the T1 has to win. So T1 I know is going to be bigger. Okay, so now let's do the equations of motion. For this one, it's going to accelerate down. We have 19.6 minus 2a equals 2a. So that's the equation of motion for this one. It's a vertical direction. For the 5-kilogram, we have the normal force. We've got 49 newtons is the weight. Then we got the frictional force, which is 0.4 times 49. What would that be here? So the friction force is 19.6 newtons. Okay? So now for this guy, we have, it's going to accelerate this way. We have T2 minus 19.6. Well, that's interesting. That one came out to be the same amount. Oh, okay, I see. You know what, let me change that. Because this one might end up being not accelerating at all here. Let's make this 0.2. And then this one will be 9.8. Okay. So it'll be 9.8. So this one, T2 minus 9.8 equals 5A. Okay. And now, what's different now is we have to do the torques on the pulley. So summation of all the torques is equal to moment of inertia of the pulley times angular acceleration of the pulley, alpha. So that we're using torque is I alpha. So this the torque due to the T1 is R alpha. R times T1, and the angle is 90. So R times T1 times sine of 90 is 1. And then the torque due to T2 is negative, because we know that T1 is going to win. They're competing against each other. So the torque due to T2 is negative R times T2 is equal to moment of inertia of the pulley, which is the Ixx, Iyy, Izz. Remember, sphere has, it's all the same. So the sphere is going to be, it's a solid sphere, so 2/5 mr squared times alpha. Now we're left with here T1 minus T2 is equal to, and then one of the r's cancels one of the r's here. We have 2/5 m r alpha. And then over here, what you can notice is that the r alpha, now we're going to use something from rotational kinematics. We learned that A tangential is r alpha when we were doing rotational kinematics, that A tangential at the perimeter of a disk is equal to the radius times the angular acceleration. So we can now make this 2/5 m A tangential. Now we can argue one more thing. We can say that the tangential acceleration at the perimeter of the disk is the same as the acceleration of the blocks, because they're all connected. Okay? Everything is connected, so the tangential acceleration of at the rim is the same as the blocks, which is equal to 2/5 ma.